Okay, today we are starting lecture number 9. We're still looking at velocity analysis, and we are sort of picking up where we left off last time. So last time we were doing the four-body chain over here using vectors like the loop closure equation. So I had a vector attached to every link, and then I ended up with my loop closure equation here. And then I wrote it in the polar form, which is with Euler notation, and then I differentiated my equation after that. So when I differentiate the equation, I end up with what we discovered last time. We just rotate each vector by 90 degrees and multiply it by the rate of change of its angle, or if you like, will be omega type thing. So over here, so that's what I did. So this vector here, the first one, I ended up adding 90 to theta 2 on top of E and multiplying by omega 2, and I did the same to each other vector. So I still have an equation, like velocity added together equation, but it looks very much like the loop closure equation, except every vector is shifted or rotated or swung by 90 degrees and multiplied by omega. Omega gives me the time thing, it's radians per second. So now I'm talking about velocities type thing. So omega is the sign that I'm doing velocity, because I'm talking about the time now, like mentioning the time in my discussion. So that's velocity. And then after that, I sort of resolve my differentiated loop closure equation, and with real into real on the left hand side is equal to real on the right hand side, and imaginary is equal to imaginary. As you know, when I do the real, I take cosine the angle by the angle, but the angle now has 90 or pi over 2 added to it. So cosine an angle which has pi over 2 added is equal to minus sine of that angle. And then when I take the imaginary part, or the component, also I have the angle 90 added to the angle. I need to use sine, but then sine angle plus 90 is equal to cosine this angle. So hence I will have in my real components, I'll have minus sines, and in my imaginary components, I'll have all plus cosines. And now every term, of course, is multiplied by the velocity, which is the rate of change of the specific angle here. All right, so now I have a velocity equation in front of me, which I need to solve to find my unknown velocities. As I said last time, my unknown velocities are actually the derivative of the unknown positions of links, right? Like every link here, my unknown position of links would be like theta 4, and would be theta 3, the two knowns, right? Theta 2 is an input data, as you know. So now I have an equation which has derivatives of those unknowns now, like theta 4 here and theta 3 here, right? And now theta 2, that's given degree of freedom, because it's a derivative of my given degree of freedom theta 2, right? Okay, so now I have my velocity equations, and I want you to look at those equations and need to solve them together to find my two unknowns, omega 2 and omega 3. And when you look at the equations, you think, yeah, they are simple and algebraic, and they are. And one interesting thing, they are linear equations. In fact, the unknowns are added together in the equation. All the omegas are added together linearly in the equations. You don't have like omega squared or cosine omega or sine omega or anything like that, like thetas. So the position model is quite difficult to solve, because when I solve a position, I try to find angles, and they are all hidden inside sine and cosine functions, and try to get them out of there to be able to find them. So the process is quite nonlinear and complicated. You have to square and add and all this sort of stuff. But when you are dealing with the velocity, you actually just have linear equations used to solve together and find your linear unknowns, if you like. Now, so I have velocities equation. Velocities are linearly added together, and they have coefficients. So every term, like omega 3 over here in this term, is multiplied by r3 sine theta 3. So you call this the velocity coefficient of omega 3. And over here, r4 sine theta 4, this is the coefficient of the unknown, if you like. You know, like in linear equations, normally, if I have a, let's say, like x1 multiplied by a11 plus x2, a12 multiplied by x2 is equal to b1, for example, right? Okay, so now my unknowns here are x1 and x2, and a11 and a12 are called coefficients, right, in mathematics. Okay, right. So I have, if I have another equation, I go a21 x1 plus a22 x2 is equal to b2. This is a set of two linear equations, very similar to my set of two linear equations over here, right, which has omega 3 and omega 4 as my unknowns, right, whilst omega 2 is the given velocity. So this is very similar to what I have in here. Of course, you can solve the set using the elimination technique we learned at high school, yes, and it should be fine. But however, I prefer to use, if you like, a linear algebra approach. Since you're doing engineering at university, you are expected to be at certain level in terms of mathematics. Then, well, I use a little bit of linear algebra in here. So if I want to solve my two equations here, we'll learn a technique, and then from this technique, I will apply it to my two equations here. So let's then arrange, I'm going to arrange my two equations exactly like I have underneath. So I have the unknowns on one side. So I'm going to have over here minus R3 sine theta 3 omega 3, oh goodness, plus R4 sine theta 4 omega 4, that's equal to R2 sine theta 2 omega 2. Just shifted those terms around, and so omega 4 was minus here. I moved to this other side. So over here I will have cosine. So I'll have R3 cosine theta 3 omega 3 minus R4 cosine theta 4 omega 4 being equal to minus R2 cosine theta 2 omega 2. All right, so I have now this set of two equations here. Those ones are similar to those ones. They are both linear, right? They are linear. So the velocity model is linear, and that's a bliss. That's something good. It's easier to deal with linear equation. The velocity model is linear, right? And then I have coefficients for my unknowns here, x1 and x2. I have coefficients for my velocity, and books refer to those are as velocity coefficients. Right now, if I want to solve those two equations over here, like in terms of using linear algebra, I arrange them in a matrix form. So I'm going to say, I'll write the equation again on the side for you. Like I have a11 x1 plus a12 x2 is equal to b1. Over here, e21 x1 plus A22 x2 was equal to B2. So we'll arrange those in a matrix form. So we'll write it like that, right? This will be my matrix form. I'm going to say over here, I'll write first, this will be my vector of unknowns, which I try to find. So I put them in this vector here, right? And then I fill in the matrices. You know, when you usually should get the first equation by multiplying the first row. So when you go, if you multiply a column, when you multiply the matrices, you multiply a column on this side, right, by the row on the side. So x1 goes into the first term here or entry, and then x2 goes to the second one, and so on. So, and I get my equation will be equal. When I do that, this will be equal to b1. So over here I should have a11 and then a12. So now imagine multiply x1 times a11 plus x2 times a112 is equal to b1, and that's my first equation. So now normally I'll have the equations to try to establish or create the matrix. Then over here my second known quantity b2. Over here on this side I have e21, and then I have a22. Now this is a system of equation. Mathematicians refer to this as matrix A times vector x or whatever is equal to vector B, right? Sort of thing. So that's linear form, or a set of linear equations, if you like, right? So linear set of equations, right? Or set of linear equations. All right, that's it. Now, if I want to solve this set, a simple way is to use something called Cramer's rule, right? Cramer's rule is like that. To solve, meaning I want to find my x1 and I want to find my other unknown x2. This is the meaning of you want to solve. So normally when you solve using Cramer's rule, the easiest way, then especially for a small matrix here, like system of equations, then it will be a fraction, right? The fraction for both unknowns, for all the unknowns, in fact, in my system, all the fraction underneath will be the determinant of the matrix. So underneath, I have the determinant of the matrix A. So that's, I put this here to calculate its determinant, right? And up here will be determinant of another matrix, right? Okay, now maybe, all right, okay, let's say determinant of which matrix, I write it here. So I'm trying here, like on this line, I'm trying to find x1. So over here, I check which column x1 is multiplied by when I expand, when I multiply the vector into the matrix. X1 is the term here at the top is multiplied by the first column. So this column, I replace it by the column on the of known values on the right hand side, because I'm trying to find x1. So I leave the rest of the matrix as is inside the determinant. And let's do the second one. Here I'm trying to find x2. x2 is multiplied by the second column. I replace it by b1, b2, and the rest stays. So now the solution is really the ratio of two determinants. So now the determinant A, how it's calculated is determinant. You go, it's A11, A12, A21, A22, right? Multiply determinant 2 by 2 matrix of 2 by 2 matrix, very simple. Just multiply here and take away that. So it's really A11, A22 minus A21, A12. This is the determinant, as simple as that, right? So, and you now, it's really important that you realize this determinant, the determinant is just a scalar quantity, right? Because when you multiply that, you get a numerical value. So this is a determinant, scalar quantity, right? So expect to get a scalar quantity on a scalar quantity. Now, when you look at the solution over here, you realize that underneath I have the determinant of A for all my unknowns. Okay, which means when I'm solving my equations, I hope A has a determinant. It was not going. I hope it's not going to vanish, because if it vanishes, then this product here, this process will give you 0. Then you end up dividing by 0, and which means you don't have a solution, or like a tricky business. I'll explain this in a second, but it's a singularity of a way type thing, and this can happen in linkage analysis a fair bit when we solve to find our omegas. We'll see what will happen in a second. So my determinant here, so when I find x1, I go, it's this determinant, it will be 1 times a22 minus b2 times a12 over my determinant, which is a11 a22 minus a21 a12, and then x2 at the top. I get a different value, so I get b1. No, I get a11 because I start from the left hand side, b2 minus a21 b1, underneath the same for all my unknowns, same determinant, a22 minus a21 a12. So that's now, this will give me the solution of my equations. This is the solution, right? All right. Now you need, as I said, you need to realize I divide by the determinant, right? Okay. So now at the situations where what will happen if the determinant is 0 or whatever, I will just maybe explain this in the context of the linkage, because what will happen if the determinant is 0? Over here, if the determinant is 0, if I calculate and determinant is 0, this means the system of equations does not have enough information for me to as what the actual values of x1 and x2 are, and I can just if you like assume different any values to get a ratio between them, but provided that b1 and b2 are actually zeros. So if the determinant of A is 0 and the values inside B is here, those values are 0, then I can just take one equation, assume any value, as the second equation doesn't give me more information, and I just assume any value for x2 and get x1. So then we said, well, infinite number of solutions type thing. So, but provided that both the determinants of A and the right hand side vector are zeros. Okay, now if the vector on the right hand side is not, doesn't have zeros in it, but then the determinant is 0, this means there's no solution. This means those equations do not link up together. There is an error in my data or something, right? This is the meaning of that. So, and I cannot solve, like there is discrepancy between the information given to me in one equation and the other equation. They are not aligned together. They are not really simultaneous equations, right? Sort of thing. So, okay. So in this case, so this is a little bit of linear algebra stuff that we may need to do. So let's then build our system of linear equations for my here my two equations. So I have, can I take, so my unknowns will be omega, so that's my unknown, that which is similar. Let's say omega 3 is very similar to x1, like it will correspond to x1, and not similar, just corresponds, and omega 4 will correspond to x2. So I can build, then my coefficients will go inside this matrix is a matrix of coefficients, if you like, and on the right hand side, instead of B, I will have the unknown values for theta 2 and omega type thing. Okay, now so let's do that. So that's one possibility. If I look at my system of equations, I can quite start saying omega instead of x1, x2. I can say omega 3 and omega 4, and that's quite fine and absolutely okay. And we'll need to do that. No worries. But what if I now, when I look at my equations and I realize that omega 3 is always multiplied by R3. So I take them together as one variable type thing. That's a possibility. And also omega 4 is always multiplied by R4. So I can take this together as one variable. Omega 2 is multiplied by R2 type thing. So let's apply that. So I can have now over here, if I have omega 3 R3, so R3 omega 3 as one variable, and R4 omega 4 is another variable. This will be matrix coefficients. Over here I'll have the known quantities. So the intercoefficients I have over here, I have minus sign and I have cosine, I have sine. So the first one will have plenty of signs. All right, so I'll have here first line, I'll have sine theta 3. This will be minus sine theta 3, and this will be sine theta 4. It came from the other side of the equation. Here I will have sine theta 2, and I can take here R2 omega 2 as constant that will be multiplied by every element in entry in this vector, right? Vector B, if you like. Okay. Now, so the second line I'll have is a cosine. So I have cosine theta 3, and over here I have minus cosine theta 4. Here I'll have minus cosine theta 2, and I hope I got those signs okay. So that's minus cosine theta 2 minus cosine theta 4. So this is my system of linear equation, which corresponds to my the example I give you over here. This example here. So that's my system of linear equation. Now, if I want to solve, so over here, then I have a matrix which corresponds very much to the matrix A. Okay, so this matrix, this idea of the matrix is a very interesting one. And so there is a matrix here. I'm going to call this matrix, call it matrix. I'm going to call it matrix J, or stands for Jacobian. That system Jacobian. All right. So okay. So that's also a mathematical term for a matrix. We'll just call it a Jacobian. But many books would call this the velocity coefficients matrix, which is quite okay, or just the velocity coefficients. But I'm going to use a mathematical term and call this Jacobian because to me it is a Jacobian. Later on, when we do more mathematics, you will understand what the Jacobian actually refers to. Normally, it's matrix of partial derivatives, and those coefficients are actually mathematically partial derivatives. And later on, you'll know what this means. You don't have to worry about it for now. So just call it Jacobian, right? So now this matrix Jacobian is quite important for me because if I want to calculate R3, let's say I want to calculate R3 omega 3, which corresponds to x1. So I use Cramer's rule. So I have to use the determinant of the Jacobian, right? So this will be Jacobian, determinant of Jacobian. And at the top here, I need to calculate the determinant of another Jacobian. Like if I replace, sorry, this will be omega 3, then I check and I'll see that omega 3 is multiplied by the first column. I replace it by the column on the right hand side. So I can have sine theta 2. I can have minus cosine theta 2, I have sine theta 4 minus cosine theta 4. Outside here, I can have a common, right? Right, that's what I can have in the outside. And then omega 4, R4, underneath will be Jacobian determinant. And here I will have minus sine theta 3 and cosine theta 3. I'm not going to touch that because it has nothing to do with 4. Then, but 4 has the other term here, the other column, they replace it by the right hand side. So I'll have sine theta 2, and I will have minus cosine theta 2 times this common factor here, right? The determinant itself of here, determinant of minus sine theta 3, sine theta 4, right? And then cosine theta 3 minus, what is it? Minus sine theta 4, something, minus cosine, or I'll just look, of course, okay, minus cosine theta 4 over here. This is my determinant here, which if I multiply this, it will be equal to, multiply those together, you get sine theta 3 cosine theta 4, take away this product here, which is cosine theta 3 sine theta 4. All right, so exactly, so this gives me, now it's cosine, sine cosine minus cosine sine. So this is sine, the difference, sine theta 3 minus theta 4. So this is the determinant of the Jacobian, sine, the difference between the two angles, right? Okay, so let's calculate the other velocities here. So let's do R2, R3, omega 3. So R3 omega 3 is going to be equal to, when I multiply those, I get sine theta 2. Okay, I get sine theta 2. Okay, here will be sine theta 2 and minus times minus cosine theta 4. So I'll put the minus outside. Cosine theta 4. Okay, and then I'll have this two together multiplied minus, they are giving me negative, minus that would be positive cosine theta 2 sine theta 4. So that's positive cosine theta 2 sine theta 4 over the Jacobian determinant, which is this difference. All right, so now, yeah, I forgot to multiply by the common factor as well. I shouldn't forget that, it's very important. Okay, so now when I do that, then I'll end up with underneath sine theta 3 minus theta 4. Over here I have sine theta 4 minus theta 2 multiplied by R2 omega 2. All right, because this is a difference here at the top. So this is, then this tells me that omega 3, if I'm after omega 3, it is R2 over R3 omega 2 and multiplied by this ratio theta 4 minus theta 2 over sine theta 3 minus theta 4. Okay, so that's the thing. So now I can tell you that omega 4 is going to be, omega 3 is going to be 0, right? If those theta 4 and theta 2 are equal. or if the difference between them is 180, right? So this gives me some idea as to when of the extreme positions of the coupler when the crank is parallel to the rocker, right? Or sort of thing, or the, and then at this point in time, if theta 4 is equal to theta 2, or theta 4 is equal to theta 2 plus pi, or the opposite, or theta 2 is equal to theta 4 plus pi, whatever. They are aligned together, or not aligned but parallel. So this is R2 is parallel to R4 at this point in time. Omega 3 will be equal to 0. This will be extreme positions for R3. There'll be the extreme or stationary position for R3. All right, okay. Now let's find the other velocity, which is omega 4. So omega 4, before we go on to find omega 4, I want you to look at this expression one more time and look at the units. So the units here on the left-hand side, on the right-hand side, those two are divided. This is length, millimeter or whatever, meter or whatever you want to use, they will cancel out. So the only units I have on the right-hand side is radians per second. And then, so that's omega 3 is radians per second because this is the units I expect to get. So if I have some extra r on the top or on the bottom of this expression, I know something went wrong. I go back and check my equations one more time. Okay, and now I can also say that omega 3 is not constant, because even though omega 2 is constant, but omega 3 is not, because my angles, all those angles here, like vary type thing. So omega 3 is not constant, has situations where it is 0 at extreme positions. Right now, if I want to get my R4, omega 4, underneath the same Jacobian I had before, which is, will apply to all of them. And then at the top, I'll multiply those. So this is sine theta 3, sine theta 2. So I'll have sine theta 3, sine theta 2, minus or plus. Here will be minus cosine theta 3 and sine theta 2. So minus cosine theta 3 sine theta 2, and that's multiplied by R2 omega 2. Don't want to forget that was a common factor up there. So this will give me sine the difference. So here I have sine theta 3 minus theta 2 times R2 omega 2 over the Jacobian of the linkage, which is that, right? Meaning that omega 4 is equal to R2 omega 2 over R4. You see this here, sine theta 3 minus theta 2 over sine theta 3 minus theta 4. And then you can tell from here when is the rocker is going to stop, at which, like both ends, the rocker will stop when theta 3 and theta 4 have the same value, or the difference between them is 180. And this is how worked the stationary positions for the rocker early on, maybe in lecture 2 or 3 or something like that. We'll discover that the crank is aligned along R3 for the extreme position to be realized on one side, and the other side the crank would be covered by R3. So difference will be that. So either theta 3 is equal to theta 2 if, so that's if, or theta 3 is theta 2 plus minus pi or whatever, then omega 4 is equal to 0. So when R2 is parallel to, but really it's just covered by R3 when the linkage is Grashof. So now I have equations for my unknowns. I have the velocity omega 3 and have the velocity omega 4, and they are function of the known velocity, which is omega 2, right over here at omega 2, and they are also function of the system angles which vary with the motion. So by this way I would have conducted a velocity analysis for the linkage, right? Because I found the velocity I'm after. What if I had a point over the linkage, like here, like attached to the coupler, for example, and I wanted to add to this point, like I wanted the velocity of a point. So I'm going, if I have a point over here, so maybe I should just draw this one more time. Okay. If I have, no, just do it here. So if I have a point here, point C, for example, and I want the velocity of point C. So if this, find the velocity of C, right? There's another part of the question added, find VC. Right, now VC, that's a point. Now the difference between VC and omega 3 and omega 4, like velocity of links, those links, the velocity was more like an angular velocity. So the link, if it rotates, when I talk about the link velocity, it's an angular velocity. A point velocity is a linear velocity, so it's meter per second in terms of units, but also it has to have two components, an x component and a y component, right? Sort of thing. So, except if it was a sliding velocity, some link sliding on another link, I just need to find the value of the sliding velocity, and I know it will be orientated in the direction of sliding anyway, right? But over here, I need, when I want to find VC, I put a little something on top of that to say it's a vector, just to remind myself. You can or you don't have to, but just that's a vector. So how to find the velocity VC of a point? All right, so what you need to to be able to do that is, normally C is rigidly attached to the link, whatever link. So you can, there is an like a vector here, like some distance, let's call it RC, for example, and there is an angle, let's call it, you want to call it anything, call it phi, a constant angle phi. Okay, as simple as that. So now you can go, you can say VC and you write the expression to do that. So this means now RC, this here, this distance RC. So don't forget that this, if you can have a vector here, a position vector for C relative to A, right? RCA, which will be equal to RC and EJ what? EJ to, and the angle will be theta 3 plus phi. So here on this side, I'll possibly put some info on this side here for you. I'll say, okay, on this side here, I'm going to say, in the color bit, so I'm going to say, okay, I have R, C relative to A, and this its length RC, and the angle of that is theta 3 plus phi, because phi is above R3. This is phi, it's above R3. So the total angle with the x-axis, from x-axis to my vector here, is the sum of theta 3 plus phi, where phi is constant. Now, if I want to find the velocity of C, so I need to write an expression for RC. So RC is like when you add R2 plus RC relative to A together, this, then RC will close this loop for you. That's RC here. And this is the, if you differentiate this vector, you get the actual velocity of C. Now, if you differentiate it only this vector RCA, you'll get the velocity of C relevant to point A. So that's not the actual velocity of C, only a relative velocity a velocity with respect to an observer at A, and who actually moves with A. So this observer cannot give you a fair assessment as to how fast C goes, because the observer actually is moving as well, right? But I have to find an expression for C with respect to a stationary point, like the origin of my Cartesian system here, sort of thing. So I had to add vectors till I get to point C, starting from the origin of the XY frame. So now I write it down here now, just expand on this a bit. I'm going to say then RC was equal to R2 plus RCA, and this was R2 EJ theta 2 plus RC EJ theta 3 plus phi. This is RC. When I differentiate that to get VC, VC is a derivative RC dt, and when you know how to differentiate, we just add like R2 for every vector, multiply by omega 2, AJ theta 2 plus 90 pi over 2, and the other one, same thing, will be R3, the RC, this will be RC, omega 3, because this is the derivative of J of the angle above, which is really here above the E. That's d, this angle by dt is omega 3, and then I add 90 degrees to the angle, so plus 5 plus 90. Now if I changed or varied, I would have actually also added another velocity for phi, but phi is constant, so it doesn't change, right? So because the link 3 was rigid, so in this case that's what I have, and I need to break those down into real and imaginary. Real is the x-axis and imaginary is the y-axis. So when I go VC in the x direction, which is really the real value, right? So that's real. Just it will be, you know how real was R2 omega 2 cosine theta 2 minus RC omega 3 cosine the angle theta 3 plus phi, and the imaginary would give me VCY, the y component, which is R2 omega 2. This was actually sine, right? Was it? I remember was because it was cosine theta plus 90, which was actually equal to sine. So here I'll have to go back and fix that, make this sine, and make this one also sine. Okay, and now this will be my cosine theta 2, and over here plus RC omega 3 cosine theta 3 plus phi. So cosine, I'll just fix this a little bit. So going to say cosine theta 3 plus phi. Now I have the x values and y values of the velocity of point C, and if I wanted VC, I would have to add, right? If I wanted and like the modulus or the length of the velocity vector, it's really VC x squared plus VC y squared under square root. And this way, I actually calculate the velocity of a point, right? This is velocity of a point, right? All that goes under finding velocity of a point, right? Sort of, I have to go to this length of the thing. But don't forget, when you are calculating, and this very important thing, remark, when you are calculating the velocity of a point, in fact, you have already calculated the velocities of separate links, individual links, and you'll use these velocities to calculate the velocity of the point afterwards. So you don't have to do extra interesting or funny calculations to solve equations together or anything like that to find velocities, because you have already calculated those when you are finding points. So my velocity analysis is more concerned with finding those velocities of links, like rotating links and sliders on top of them and stuff like that. And then I'll use these values later on to find the velocities of any point attached to any link after that. Very easily, straightforward calculations. I just need to realize for points I am calculating x and y values, and I need to know how the point is sitting on the attached to the link in terms of the distance from on the link and the angle from some reference line in the link, like angle phi in this case, and so on. All right, okay. So now, so that's once I have done my velocity analysis, I can find velocity of a point. I'm just possibly right here. Velocity of points. Okay, so and we looked at point C attached to the coupler in the 4-body chain. All right, now I want to go back for a second and look at my Jacobian and just discuss what if the Jacobian was equal to 0. Because now when I calculated my omegas, if you realize now, if you remember, we used Cramer's rule. Whatever rule, you end up with the same mathematical expression. So if you have a problem using one method to find velocity or whatever, you'll have the same problem if you use a different method anyway. Okay, so now what I'm saying is what will happen if the Jacobian is equal to 0. Now I have both, all my unknowns are divided by the one Jacobian. So that's if it's 0, this will really will mean I cannot have proper calculations. Okay, but there is a physical meaning for the 0 Jacobian. Okay, it means that if now the vector on the right hand side, like this vector here, is always not 0, like in this case, for my 4-body chain, I have a crank. The crank is capable of doing 360, so I take it as it's always rotating. It's not stopping. All right, so this means all this vector here will always be non-zero, right? I don't have omega is of course a vector by like virtue of geometry or trigonometric identities is not 0 because you never have sine and cosine 0 in the same time. So that's so one of them will not be 0 at least. And also, but what will make this quantity, the whole vector here 0, is if the velocity, if the link stops, right? Or at an extreme position of the link, at an extreme position of the link. Okay, so now, and then in this case, then what will happen if the link doesn't have an extreme position like this crank? No extreme, it rotates all the time. If the Jacobian is equal to 0 during the calculations, this means at this specific value of θ2, the linkage has actually jammed, has ceased. It cannot keep moving because so this means the Grashov is like it's not the linkage is non-Grashov or whatever. This applies to all linkages, by the way, right? So okay, so if you know that the vector on the right hand side is not 0 because it should keep rotating, you should expect to get a non-zero Jacobian all the time. You don't know. Now you need to understand that the value of the Jacobian, the determinant, is not constant because that's here the determinant of the Jacobian is this expression here, this value, right? This is Jacobian determinant. It's sine θ3 in this linkage, sine θ3 minus θ4, and these values are they change, so the Jacobian changes, right? But during these changes, when it's changing, it should never, the determinant should never be equal to 0 at all, because this means the crank cannot keep rotating, or things will start breaking. So the length don't work together to give you a proper linkage or a Grashov linkage. Okay, so that's a sign the linkage is not going to rotate. If the thing is 0, the Jacobian determinant is 0, and the right hand side vector is not 0. But if on the right hand side here, instead of θ2, I decided to have theta 4, for example, on the right hand side. I can rearrange my equation, no problem at all. My equations are actually here. I could move things around to have omega 4 on the right hand side, right, and have omega 2 on the left hand side, and then my Jacobian will have here, instead of that, I'll have omega 2, and here will be omega 4, right? At this point in time, if the Jacobian for this arrangement is equal to 0, this means omega 4 is equal, the right hand side of the equation is also equal to 0, and this can make sense to me because I know at some point in time omega 4 is going to be equal to 0 because the rocker has extreme positions. So if I place a vector on the right hand side with a velocity of a link, I know it's going to have extreme positions, then this Jacobian, when it's equal to 0, will give me those extreme positions. Okay, so it will use this Jacobian as a tool to study the mobility of the linkage as to whether you have extreme positions or not, or whether the linkage is going to stall or not. So then the Jacobian itself is a very powerful tool in that sense. Now, so when you draw the Jacobian against theta 2, because the Jacobian is also something you need to draw against theta 2 when you are designing a linkage, because if you draw the Jacobian, the determinant against theta 2, you should always get a value either above 0 or below 0. Like for it can be always positive or always negative. The Jacobian must be, all right, maybe I should say that. So the Jacobian must be always must be always negative or always positive for the specific linkage for a given linkage. But so it cannot go it cannot be equal to 0. So it cannot be equal to 0, right? So cannot cross, because if it's going to cross from negative to positive or from positive to negative, it will have to be equal to 0 at some point in time as it is crossing, right? So I'm saying that just to say it cannot take a 0 value. But as I said, let me qualify what I said. Which is Jacobian? The Jacobian which you get if you place the crank on the right hand side of the equation. Okay, this is a specific Jacobian that cannot be equal to 0 because the crank should be rotating all the time, and if it's equal to 0, this means omega of the crank has to be equal to 0. This means the linkage has stalled. All right, but the other Jacobians, if you have theta 4 or omega 4, omega 3 on the right hand side, this one I expect it to be equal to 0 at some point in time. No worries at all, because I know those links have extreme positions, and I know this, I can take the Jacobian which corresponds to those if you like links, and equate it to 0, the determinants equate it to 0 to find the angles at which those links will be equal to 0. And in fact, those Jacobians are, you know what, they are the ones I had on top of those ones here. These are the ones on top of um, um, J when I calculated omega 3. This Jacobian would be the one I get if I place omega 3 on the right hand side of this equation here. This will be the system Jacobian, which would be underneath if I'm doing Cramer's rule or something like that. All right, so let's give this Jacobian a name. Let's call this J theta 3, right? All right, let's call it J theta 3 because corresponds to theta 3 on, like it's missing theta 3 because, right? And then this one, if I equate it to 0, it will give me the extreme positions of link number 3. And this one, I want to call this one J theta 4 Jacobian, which corresponds to theta 4, this one here. So that J theta 4, because now it doesn't have theta 4 in it, and I would be getting this Jacobian, J theta 4, I would be getting this one if I arranged my initial equation up here to have omega 4 on the right hand side. This would be the main Jacobian of the system. Currently, the main Jacobian of the system is the one when theta 2 is on the right hand side, like in this case. And this is the Jacobian I got. Let me call this Jacobian, give it a name. I'm going to J theta 2, J theta 2, J theta 2. And those will be the ones that will be interested in most cases, because I don't want this to be 0. If J theta 2 is equal to 0, then the things will store type thing. So this is J theta 2. All right, so over here, I'm going now this point time to qualify my said here what I said before by being more specific to say this is J, my argument applied to J theta 2. There has to be always positive or always negative. Okay, one like in the 4-body chain, the negative Jacobian will correspond to another, or the positive Jacobian, if you like, will correspond to an assembly. You know how the 4-body chain has an assembly and then and two possible assemblies. All right, maybe I can quickly, in the few minutes left, I'll just insert the picture I had for a 4-body chain from previous. Okay, the image I had here. And just to show you what I mean. So here I have, this is my 4-body chain. All right, so okay, so now this is my 4-body chain. I can just maybe flatten this for a second so it doesn't move around. Okay, that's 4-body chain. So I have, this is maybe I have two possibilities for the assembly, right? So remember, this was assembly number 1, or you can do whatever two, that's not a problem, call it whatever you like. And this will be the second assembly. Okay, and we talked about this later earlier in the process when we discussed the position analysis. And then those two assemblies, so let's say this assembly I'm talking about. Okay, the two assemblies, let's say, by the way, I just realized here that those that's equal because that's one radius. That's also equal because that's the radius of the R4 angle. So this means I have some angle here. If I have, remember this angle, we referred to this angle previously as a transmission angle, if you remember it. The angle mu, right? That's transmission angle mu, which will be equal to the transmission angle of the other linkage as well. The other assembly, right? That's mu as well, right? That's interesting. All right, okay. Now, what happens here is, what if I wanted to find, remember the Jacobian J theta 2 was equal to, when I did my analysis, J theta 2 was equal to sine theta 3 minus theta 4 or something like that, wasn't it? I wanted to know what this actually means. Sine theta 3 minus theta 4. Yeah. Theta 3 minus theta 4. Okay, that's fine. So does this mean, does this have like some meaning or something like that? Let's see what's happening here. So my angle theta 3 is this angle. This is theta 3 because measured from positive x direction. And my angle theta 4 was actually this angle here, isn't it? For this linkage, right? Then I can say, I'm just trying to find if I can relate those angles together. So what if I extended, so this is like R3. So theta 3 is still this angle here. This is theta. This angle is actually equal to theta 3. And I want to see if I can use this angle theta 3 to and maybe mu to make some understanding, like, you know, of that of J theta 2. Now this value here, this value, this specific angle, I can relate it to theta 4, because don't forget that's also the x-axis. So they add together this angle and the theta 4, they add together to 180. So I can say this angle here is equal to pi minus theta 4. Exactly. So now if I add the three angles together, they will give me an expression. They'll give me pi. Yes. So theta 2 plus pi minus theta 4 plus mu, which is the transmission angle between R3 and R4, they give me an expression which is pi. So if I go, then theta 3 plus pi minus theta 4 plus mu, that's equal to, here, this will be equal to pi. The three angles will be equal to pi, right? Those three angles equal to 1 pi. Then pi cancels out from both ends. This means then theta 3 minus theta 4 is equal to minus mu. Okay, so this means the Jacobian theta 2 is equal to sine minus mu, which is minus sine mu. So this tells me my Jacobian here is going to have a negative value, but the value is not really, doesn't, the positive or negative is not important, right? But now this tells me that, remember that the significance of the angle, transmission angle mu. I'll just put down here that mu is a transmission angle. There is a transmission angle. And the significance of it, if you remember, we said the force transmitted F times R4 sine mu will give me the torque transmitted to the rocker. And then, so if, like, this means if sine mu as a function is equal to 0, no torque will be transmitted, right? Sort of thing. So, and in this case, this is exactly what will happen when R3 is aligned with R4, and then this angle mu can be 0. And remember, we wanted sine mu to stay as close as possible to 1, because it's the maximum value of sine. I mean, 1 or minus 1 is not important, but close to the absolute 1, sine mu. And this is important because the maximum sine, I want to get the maximum torque I can get, and I want this sine to be close to 1 as possible, because maximum possible value for sine mu is 1. And then if the link 3 and link 4 are aligned together, this means Jacobian is equal to 0, because mu will be either 180 or something like that, and then the linkage is going to stall. So because no torque will be transmitted, so the link is going to stall. So everything, when you just put everything together, you can develop a good understanding of what's happening. Then when you plot the Jacobian, again it's theta 2, right? The Jacobian here, the determined, then you'll have a negative value here. It should not, like, so just right. So this just tells me, I think just a negative here means that it doesn't have like any connotation apart from the direction of the torque or something like that. But the value, the absolute value, is what I'm interested in. So this will be theta 2. There is the other like assembly. What will be the value of this assembly? I want you to calculate it to see if you get the same Jacobian. The Jacobian would possibly be the same in terms of theta 3 and theta 4, because my angles are exactly the same. But the situation in terms of relating this value, like theta 3 and theta 4, and relating them to mu, may be slightly different. Let's see if we can do this together and find the Jacobian of the other assembly, just out of curiosity. Okay, so now I can, in this case, I'll I will have you can use a different color, maybe just to see, yep, so to find my new theta 3. So mu theta 3 for the other assembly will go all the way down like that. So this will be my new theta 3. This is mu. This is my new theta 4 will go down like that. This is my new theta 4 as well. Right, so if I draw parallel to x-axis like that, so this angle here, this little angle, is going to be theta 4 take away pi. That's correct. And this angle here is going to be 2 pi take away theta 3. This angle here. All right. So so this angle here, which is this angle, is equal to that angle. So this is theta 4 minus pi. Now if I add those angles together, I'll get pi. So if I add for this second assembly, so this is for assembly. So what I did here was assembly 1 previously. So I'll just assembly number 1. So let's do assembly number 2. I will have assembly number 2. I'm going to have 2 pi minus theta 3, which is this angle here, right? Plus mu plus theta 4 minus pi, they add up to pi. So this is just because they are the angles on one side of, like here, like that, those are parallel and intersected by one line. So the angles inside add up to 180. And this is the rule that I used, or the law that I used here. So now I can find that theta 4 minus theta 3. I'm trying to find theta 3 minus theta 4. Okay, so I can move them to the other side. Now if I move, those pi's will cancel together. All those pi's cancel together. Then I can see here that theta 3 minus theta 4, when I move them to the other side of the equation, will be equal to mu. Exactly, straight away. So this means Jacobian theta 2, the determinant, which is sine theta 3 minus theta 4, is equal to sine mu. This is the second assembly. The Jacobian is equal to sine the angle. So the first assembly was equal to minus sine the angle. The second one is sine the angle. So this will be assembly 1 and the other one, but they are mu. Of course, mu is always equal on both sides because of those triangles and the circles intersecting. So the Jacobian is always the same for the same theta 2, but one of them would be sine mu and the other one is minus sine mu. So one of them is for one assembly and the other one is for another assembly. So this is assembly number 1 and the other one is assembly number 2. All right, so I think I'll just leave it here, and then next time we'll do yet another example, velocity analysis again, using those vectors, and we'll start looking at the vectors, how to differentiate the vectors when the length is changing as well. Okay, now please try to repeat this example by yourself and see if you'll get similar answers. And if you are in doubt about anything, drop us a line either on Moodle or by email. Okay, good luck and bye for now.